By the way, here's an interesting exercise. I don't have time to do it, but you can ask the following question. If you tell me that every point there's unique entropy, then the entropy difference between 2 and 1 should be independent of how I go from 1 to 2. You understand? So I could find the entropy another way. Let me show you another way that's easy for you guys to work out. Come down like this and go to the right like this and find the entropy change. You will get the same answer as I got on this side. Here, let me tell you how it works. Call this intermediate point, give a subscript 0 for all its parameters. Then in this step, when you come from here to here, the entropy change will be, let's take 1 mole of a gas. When I go from here to here, then for 1 mole of a gas, the heat transfer dq is CV dt, and I divide by t, and I do the integral from T1 to this point T0. That's the entropy change here. Then in the horizontal part, since I'm going at constant pressure, I go Cp dt over T from T0 up to back to T1, because this T1 and T2 are the same temperature. I have to add all these to get the entropy change. Now it's a two-step process. You come down, because you're at constant volume and you're doing something to the gas, dq is Cv dt. Horizontally, you're at constant pressure, dq is Cp dt. That's the definition of specific heat at constant volume, constant pressure. But notice the following. Cp is equal to Cv plus R. So put Cv plus R here and look what you get. Then you get Cv times log T0 over T1 plus log T1 over T0, which we can write it as the product here, plus R log T1 over T0. In other words, this log is log of T0 over T1. The next log is log of T1 over T0. And log A plus log B is log of AB. But when you do this, look what happens here. This all cancel. Log of 1 is 0. So total entropy change is R log T1 over T0. But for a gas at constant pressure, using PV equal to RT, this ratio of temperature is also the ratio of the volumes. So this one, I'm sorry, I should write it more carefully. When I say T1, I really meant the temperature at this point, second point. So that temperature over this temperature is also that volume divided by the initial volume, which is V1. See, this is a confusing problem because T1 happens to be T0. The correct way to do this for me would be to write T0 over T1 times T2 over T0, then realize the fact that a T2 and T1 are equal because I'm on an isotherm. That's what I should have done. So I should cancel this factor because T2 is T1. But here T2 over T0 is V2 over V0, which is V2 over V1. That's, of course, the entropy change I got in one shot here. All right? So we have now learned how to find entropy change. We have no idea what it means. It seems as if when you heat something, entropy goes up. When you cool something, entropy goes down. That's certainly correct because delta Q is positive for heating, and you divide by T, you may get a logarithm, but we know at every infinitesimal portion I'm adding positive numbers. And when I cool things, it goes down. Why not just call it temperature? Why do you need this new concept called entropy? So that's what the rest of the lecture is about. It's a very, very powerful and beautiful concept, so I want to explain it, make sure I get it right. Here is now the result for all this hard work. Remember, I told you there are many, many, many phenomena that seem forbidden in our world, and we're not quite sure what law to invoke to prevent all of them from happening. Do we want a law for each one that says if you drop a bottle and it shatters, it won't come back? If you drop an egg, it won't come back. If you let hot and cold mix, they're not going to unmix. Or if you let a gas trapped in half a room escape to the whole room, it'll never untrap and go back to half the room. A lot of things happen one way but not the other. And I said, I'm looking for a mega law that will prevent all these things from happening. So now I'm ready to state that law. So this is the third law. I mean, the second law of thermodynamics. Carnot said it one way, but I'm going to say it in a way that's very, very general. The second law of thermodynamics says delta S for the universe is either 0 or positive. There you have it. That's the great law. The law says, take any process. If at the end of the process, the entropy of the universe is bigger than it was before, that will happen. If the entropy of the universe is smaller than it was before, it will not happen. Now, we have to make sure that this law has anything whatsoever to do with all the other things we have studied, and I will show you this will forbid everything that should be forbidden and allow everything that should be allowed. So let me start with the most obvious formulation. Mr. Carnot's version of the second law was that you cannot have a process in which some heat Q goes from a hot body to a cold body. I'm sorry, this is allowed, right, according to Carnot. This is not allowed, right? Heat can flow downhill, cannot flow uphill. Let's see the entropy change in the universe for the two cases. In this case, for this guy, the change in entropy is the following. The upper reservoir lost some amount Q, so delta Q is a negative number, at some temperature T1. The lower reservoir gained Q at temperature T2. Now, what's the overall sign of this? Think about it. T1 is bigger than T2, so this negative number is smaller than this positive number. So the whole thing is positive. That means it's allowed. It's okay. By the same token, if you take this process, when heat flows uphill, then this reservoir loses some heat Q at temperature T2. The other one gains heat Q at temperature T1, but this is clearly less than 0 because this positive number is smaller than this negative number. So there you have a very simple example where if heat flows the wrong way, the entropy of the universe goes up. And it's very simple. It's because it is true the heat loss of this guy is the heat gain of that guy. That's the law of conservation of energy. So energy doesn't change, but entropy changes. Because for entropy, it's not the heat transfer, it's heat transfer divided by temperature. Therefore, a heat loss at one temperature and a heat gain at a lower temperature don't cancel when it comes to entropy. In one case, the entropy goes up and it's allowed. In another case, entropy goes down and it's not allowed. Okay, so let's try. So that's certainly one process that you know should not be allowed, but it's forbidden by the third law by a computation of entropy. So the reason when you put a hot and cold body together, heat flows from the cold to the hot, from the hot to the cold, is because that's the way the entropy will go up.